Hi, everybody. This marks a pretty special occasion. If I've calculated right, this is our last official lecture for AP Physics C, because this will wrap up rotation, and after this, we'll review for this unit and then start reviewing for the actual AP exam. Just a quick kind of brain warm up to get yourselves going. So I've got two images here. I've got five different particles. All of them have the same momentum. Here's particle 1, particle 2, particle 3, 4, and 5. And I want to know their angular momentum with respect to O. So you can either use this O here for these two, or this point O for these three objects here. Please notice that 1 and 3 are lined up. This O is lined up with this O, and 2 is lined up with 4. So my question is which one of these has the largest magnitude of angular momentum with respect to O? And the answer is, hopefully you figured it out, is both 1 and 3. Why? Oops, I realized I forgot, don't think I have my pen turned on. Why? It's because of the distance between, or I'm going to use the perpendicular distance, between point O and those objects. So again, if you look at this one here and I follow along the velocity vector, here is my perpendicular distance, not quite right. There's our perpendicular for that one. And for 1, you have that same perpendicular distance over here. So they actually tie for largest magnitude. Which one of these have negative angular momentum with respect to O? For that, you're going to have to do the right-hand rule. Remember, the angular momentum vector is equal to R, I'll use capital R cross, sorry, my bad. R cross, I'll use M momentum here, MV, or you can also, yeah, that's probably the easiest way, or write MV down there. So in this case, if you do your right hand, starting from O out to where the particle is, and then if you can easily bend your fingers in the direction of the momentum vector, your thumb points in the direction of the angular momentum. So which one of these points out of the page? I'll give you a second to try this. You might want to pause the video. But the answers are 2 and 3. When you get done with this, your thumb's pointing into the screen when you do R cross momentum. And which one of these have zero momentum with respect to point O? The answer, of course, is 5. Why? There is no perpendicular distance, or R perpendicular in this case is 0 for point number 5. All right. So we get into chapter 11 here, which is talking about rolling and slipping. And you already know the relationship V equals omega R is valid for any point on a rotating object. So if you look, for example, at a point on the rim of this wheel, yes, it's true. Omega times R does give you that. Oh, by the way, there is a bit of an optical illusion on this one because of the frame rate. This wheel is actually rotating this way at a fairly large rate. But because we're taking images, you get a stroboscopic effect, and it looks like it's going backwards. And the hub looks like it's going forward just barely based on the frame rate. But inside of a rigid object, yes, this is O is valid. But I've got a question for you. Does it always translate or correctly relate the translational or forward speed of a tire to its angular speed? And the answer there is, think about it for a brief moment. Can you have a tire rotate without the car going forward? And the answer is, yeah, you can actually. Think about it for a brief moment. If you've ever seen a sports car take off or a drag racer, when it first takes off when the car is stationary, you can have the wheels spinning without the car going forward. It burns out, in which case we've got a large omega, but a zero or minimal velocity. So in that case, you can't use this to relate the two quantities. The outside radius of this tire is not equal to that part. And in the same question, can you have a tire moving forward with translational velocity, but have no angular speed? The answer is you betcha. If you've ever seen somebody whose car does not have anti-lock brakes and they suddenly slam on the brakes, what happens? The car slides forward with some velocity while the wheels actually stop moving, and it just slides along the ground as it moves forward. And so in that case, you've got velocity, but no omega. And so you've got to be careful with this equation. We've always sort of been kind of sloppy with it in honors physics or AP Physics 1. We assumed that was always valid all the time. Well, it is inside of a rigid object, but not necessarily for an object that's rolling. Depends on what's happening. If it's slipping, then that's not true. So, take another example of this. Most of you have been bowling before. When you release the bowling ball, you give it a large velocity, but almost no omega, no angular velocity. And the ball actually slides down the lane. And while it does that, friction produces a torque on the ball that slowly increases its omega and decreases its velocity until it begins rolling without sliding or slipping. At that point, V is equal to omega R. Take a quick look at this video. In the video here, a robotic arm actually gives the ball a reverse effect, a large omega with a small v. And if you can see, it's actually spinning faster than it's moving. And towards the end, it finally actually picks up speed in the direction that it's spinning and actually turns. Actually, entirely time, it's slowly gaining velocity in that direction, which gives it a nice curve, which is kind of cool. So, rolling with initial slipping, there's a couple of possibilities. One is the one we talked about, where you normally when you bowl, you give it a large forward velocity, but almost no omega. So velocity is great, or much larger than omega. What's going to happen here? The force of kinetic friction between the floor and this is going to be acting against the slide. Remember, friction always acts against the slide or potential slide. And that friction, because it's acting against the motion, is going to decrease your velocity, but it's going to increase omega. Why? Here's the center of mass of this object, and you have a radius, and so this thing is going to start rotate or angular accelerating this thing this way, which is going to begin to get it rotating this way as it goes. You can also, like you saw in the video here, get it where it's omega is much larger than that. Actually, I should write a little note here. This is bigger than that. It's omega r bigger than v. You can give it a top spin, so it's actually spinning faster than it's moving forward. In that case, this bottom part's sliding against the floor this way. Friction acts against the slide or potential slide. In this case, friction's acting forward. What's that doing? It's actually producing a negative torque on our object, which means it's actually angular accelerating it this direction, which means what's happening? This torque is decreasing omega. At the same time, this force is accelerating this object, regular acceleration, this way. So it starts gaining velocity as it loses omega. Objects roll without slipping until this equation is now true, that the velocity of the center of mass is equal to the omega of the object times its radius. So here's a real practical example. A solid disk of mass 5 and radius 0.1 slides with a velocity of 5 and initial omega equals 0. If the coefficient of friction is 0.2, what's the acceleration of the disk? Well, I'm not going to put the normal, the force of gravity is going to be 49 newtons, normal force 49 newtons. And the force of friction then is just 49 times mu. Well, 49 times 0.2 gives us a force of kinetic friction acting at this point of contact of 9.8 newtons. So what's the acceleration of our disk? Just F equals ma. Net force is negative 9.8 newtons equals the mass 5 times a, and our acceleration is that. And now the second question, though, is what is the angular acceleration? Well, this force is actually producing a torque on this object. How do we solve it? Well, torque is equal to I alpha. In this case, the torque is the force of friction times the radius, equals I, because it's a disk, it's 1/2 mr squared, all times that, ignore the little point here. And if you solve that equation, you get that the angular acceleration is 39.2 radians per second squared. All this is happening while it's sliding. So my next question is, all right, so we know the acceleration. What's the velocity at any given time until the point where it stops sliding? Because it's changing all this time. Well, just using v final equals, that's supposed to be v initial plus at. V final equals the initial velocity 5 minus or plus the acceleration negative 1.96 times t, or we get the velocity at any given time until it stops sliding is 5 minus that. Likewise, we can do a similar thing with omega. And again, that's supposed to be omega initial. I missed it. In this case, the initial omega is 0. We know the angular acceleration is positive 39.2 radians per second squared. And so we get omega at any given time up to it stops sliding. It increases at this rate. So the question is, at what time will it stop sliding? Well, we know when it stops sliding when this equation is going to be true. So plugging in our equation for velocity at any given time here, and our equation for omega at any given time here, and plugging in our radius from up above here, if you solve this equation, you'll discover that when does this become true? It becomes true at t equals 0.850 seconds. What's its displacement during this slide? At this point, I'm just going to use this equation, v0t plus 1/2 at squared, plugging in our numbers. Initial velocity is 5, time is that, acceleration is that, and you'll discover that the displacement during this time is about 3.54 meters. In other words, it's going to slide 3.54 meters before it rolls without sliding. And this is kind of the same effect. You get this whole idea of, ooh, okay, I get it. It's kind of cool. You could figure out a bowling ball if you wanted to. If you knew the mu of the lane and your rotational inertia of your object, yeah, you could easily solve it. So what's really happening with an object that is rolling down the street? Well, there's something interesting going on here. Take a look. If you just have a wheel that's rotating around its center with some velocity, you end up with this kind of situation where the velocity here at the bottom would be going in a negative velocity, the top here going with some positive velocity, relative to this if we assume that this velocity is 0. But now, what's really happened to the wheel? The wheel's just not spinning, it's also moving along the ground. Well, if it was just translating, if this thing was just sliding along the ground with it rotating, then all the points would be moving with the velocity of the center of mass. For an object that's rolling, what's really happening here is something a little bit more bizarre. It's the sum of these two. Rolling motion is really a combination of pure rotation and pure translation. And what happens here is this. We literally add these. So this point plus this point gives us 0 down here. This one plus this one gives us just the velocity center mass. And these two up here gives us that the top of the wheel is actually moving twice the velocity of the center of mass. Now, the part that drives everybody crazy is the fact that the bottom is at rest at 0. You're like, no, that's not true for a rolling wheel. Yeah, even if you watch a car wheel going down the pavement, the point at which it's in contact literally has a velocity of 0. You're like, no, the wheel's moving forward. Yeah, a little bit later, this point's going to be in contact with the road down here, and it's also going to be at rest relative to that point. The bottom of the wheel literally has no velocity. And now we can use that idea to sort of quick calculate or show you one of the things we've always assumed, but I've never proved to you. What if I take a look at this point right here and think about the whole wheel is rotating relative to that point? And I ask, hey, what's the kinetic energy? Well, you know, rotational kinetic energy, 1/2 I omega squared. And if you solve this, I guess remember, because the center of mass is up here and my pivot point's down here, I've got to use the parallel axis theorem, which states you got to use the rotational inertia through the center of mass plus mh squared, where h is how far I moved this away from this point. In this particular case, I is going to be this, and h becomes r squared. And so this whole equation, kinetic energy, becomes that. Well, I can distribute these a little bit, and I end up with this, 1/2 I center of mass times omega squared plus 1/2 mr squared omega squared. And I can replace omega, remember, with v over r. And then suddenly this becomes this. And you're like, wait, I recognize this. Yeah, here's where it comes from. This is RKE, and this is over here KE. And that's why we say a rolling object, like an object rolling down a ramp, has both forms of these energy, or both forms of these, just the kinetic energy of the center of mass in motion and the rotational kinetic energy of just the rotating object. And this kinetic energy is the sum of those two quantities. But that's where this actually comes from. Besides using, I guess I should write on here somewhere, besides using the idea of omega r is equal to v for non-slipping objects or non-sliding objects, you can also use the equivalent of that one, which is alpha r is equal to a translational. And let me show you this real quick. Most of you have played billiards before or pool, and most of you know that when you're hitting, this is a cue stick, hitting the cue ball. Here is its center of mass. If you hit it right here, that if you somehow put your cue ball right in line with this, like the soccer ball we talked about before, this thing would simply have a velocity this way, but it would actually have initial omega of 0. What would happen? It would slide, and the felt on the table would eventually make it roll after it slid some distance, sort of like what we talked about. But here's the question. Is there a value of x that you could hit it so that it would have no, or that it would not slip? In other words, this would give it enough torque, think about the torque here, that it would angularly accelerate at the same rate it regularly accelerated. In other words, this would be true and it would not be slipping. So take a quick look at this. So for rolling without slipping, this also has to be true. Acceleration has to equal angular acceleration times r. So let's first of all figure out what the acceleration would be. Well, F equals ma, or the acceleration is simply equal to this force divided by the mass of the ball. Easy enough. And now for the torque and alpha, torque equals I alpha, the rotational equivalent of F equals ma. In this case, the torque generated is going to be x, which is the perpendicular distance between the force and that, times the force. So this becomes this. And I for a sphere is 2/5 mr squared, and of course alpha stays alpha. Simplifying that down a little bit, we get alpha equals this quantity right here. Just solving that equation. Once we have that, we can take those two and plug them in over here. So we know our regular acceleration is this, that's from up over here. And we know our angular acceleration is this from right over here. And then the radius of our thing, of course, is r. If we solve that, we get that, or solving it, we get x equals 2/5 of r. Notice it doesn't even matter what the mass of our ball is. It's just that. It doesn't matter what the force is, doesn't matter what the mass is, it's just that. So below that point, you're going to give it more velocity than omega. If you're above 2/5 of the radius, you're going to give it a top spin. You're going to give it more omega spinning this way than velocity. So you can actually kind of control where the ball goes. And yes, you could figure it out also for a hollow disc. Hint, it's going to be 2/3 of r if you haven't quite seen the pattern yet. And now talking about a ball rolling down a ramp. I'm so sorry, they're vacuuming outside my room. I hope you can hear this. We haven't really done a really detailed look at this. We've done it with energy before. But on a ball on a ramp, what do you have acting on it? You've got the force of gravity this way. You've got the normal force acting this way. But there's also has to be a force of friction acting up this way. And it's static friction if it rolls without slipping. It never slides down the ramp. And you're like, Ray, there's friction acting here? Yeah, if there was no friction, these two forces would not produce a torque on this object. It would not begin to angularly accelerate. So there's got to be this to actually cause this thing to rotate. So how do you solve something with both angular acceleration and linear acceleration? You're like, no, it can't be. Yeah, you got to do both equations. In this case, let's look at F equals ma first. What's the net force on our object? Well, it's this component, the component of gravity acting down the ramp. I know in this diagram, normally I put it down here. Minus the force of static friction. And please ignore the magnitude of these. Which one's larger? This one has to be bigger than this if this thing's accelerating down the ramp. Equals ma, mass times acceleration. And over on this side, what's the torque? Well, the torque is going to be the radius of this thing times this force of static friction equals I times alpha. And now let's go play with this a little bit. Solving this side for the force of static friction, moving that to the other side, and then moving MA over there, we get this. And now I can move that over to this side. So I've taken this quantity right here and plugged it in over here. And so we get this. And now playing a little bit, I'm going to replace alpha with A over R. And I apologize for the font here. Alpha and A look a lot alike. That's A, that's alpha. And so I can get this equation right here if I move the R to the other side. So this is IA equals this quantity. And now, if you distribute the R squared, we get this. And then playing with it a little bit more, let's see, what did I do here? I'm going to move this term to the other side so I get all my A's together, because I'm going to try to solve this for the acceleration. If I do that, factoring out these two terms gives me this, or I get A equals this. But that's typically not the way it's written. Usually what happens is, because we've got mr squared both here and down here, most books divide it by mr squared, giving us then just g sine theta over 1, this divided by mr squared becomes 1, plus I over mr squared. And this is true for any body rolling down a ramp. And one of the questions I always get asked is, should we memorize this equation? The answer is no. I don't even keep it memorized. I have to derive it every single time. You're like, really? Yeah. But it does actually help us solve a few things. Remember before we talked about the rolling Olympics? Which one of these gets down faster? Well, their accelerations down the ramp depend on the rotational inertia's I. The bigger I is, the bigger the denominator becomes and the smaller I gets. Which of these objects has the greatest rotational inertia? The answer is, of course, the ring. It's mr squared, followed by the cylinder, which is 1/2 mr squared, followed by the sphere, which is 2/5 or 0.4 mr squared. So which one gets down the ramp first? Well, the sphere, followed by the cylinder, lastly by the ring, because it has the greatest rotational inertia, biggest denominator. All right. Talk about things like this. We can now actually solve for like the velocity of the bottom, the force static friction on a ball rolling down, assuming it's not slipping. What can we do? Figure out the velocity of the bottom, pretty straightforward, just using energy conservation. Sorry I didn't plug it all in. At this point, you could plug in g and the height over here into this, and you could very quickly solve for the velocity. And using our equation we just derived a moment ago, you could easily figure out the acceleration. Negative because it's acting, well, I don't know. I guess negative because it's acting to the left here. Sorry, I'm just interested in the magnitude. I'll make them both positive. But then ask the question, what's the force of static friction? How do we solve that? We can use F equals ma. In this case, we know this force minus this force has to equal ma. We know the acceleration in this case is this right here. Plugging it in, we can very quickly solve for the force static friction. It's going to be 2/7 mg sine theta. And you should be like, okay, got it. So now how do we actually use this on the AP? Well, here's a free response question from a few years ago. A solid cylinder with mass m, radius r, and rotational inertia 1/2 mr squared rolls without slipping down an inclined plane shown above. The cylinder starts from rest at a height h. The inclined plane makes an angle theta with the horizontal. Express all solutions in terms of the given quantities. A, determine the translational speed of the cylinder when it reaches the bottom of the inclined plane. So just using energy conservation, mgh equals what we talked about before, 1/2 mv squared plus 1/2 I omega squared. And solving that just real quick, plugging in v over r for the omega gives us this, or we end up with that. Or solving for the velocity, we get the velocity at the bottom is square root of 4/3 gh. All right. On the figure below, draw and label the forces acting on the cylinder as it rolls down the inclined plane. Your arrow should begin at the point of application of each force. Well, we've already talked about the fact that if it rolls without slipping, there has to be a force of static friction acting up the ramp, and that acts at the point of contact between this thing and the ramp. Of course, there's the force of gravity. It acts down from the center of mass of the object. And now here's the tricky one, tricky because it's messy to draw. The normal force acts at the point of contact as well, and it acts upward this way, perpendicular to this. That doesn't look very perpendicular, but it should be. And it should be, yeah, it probably should be larger than that, but you get the idea. But there is a net force down the thing and a net torque. Show the acceleration of the center of mass of this system while it's rotating is given by that. You could do at this point F equals ma and torque equals I alpha and solve these simultaneously and get this answer. But we can cheat a little bit. Why? Because we already know the velocity at the bottom of the ramp is going to be this number right here from beforehand, we can just use this equation. But we need to figure out what the length of this ramp is. Well, it's pretty easy. We're given theta, so we know that the sine of theta is equal to the opposite side, h over the hypotenuse L, or L is equal to h divided by sine theta. So if we use that idea, we can plug in all our numbers. V final squared is this, that's our answer before without the root symbol. Our initial velocity is 0, 2 times the acceleration, and our delta x is the length, which is h over sine theta. Solving that, we get exactly what they said we should get, but without a lot of algebra. D is a little bit more ugly. Determine the minimum coefficient of friction between the cylinder and the inclined plane that's required for the cylinder to roll without slipping. Well, we know F equals ma has to be true, and we can solve then for the force of static friction. Remember, the net force on our thing is mg sine theta minus the force of static friction equals ma. We know the force of static friction should be equal to mu s times the normal force. Normal force is going to be mg cosine theta. And we know our acceleration is given by this from right up above here. You'll notice that mg cancels out very nicely from all three terms. And if you solve this, you'll have to subtract 2/3 sine theta from sine theta over here, move cosine over there, and solving for mu sub s, you'll discover that mu sub s has to be at least tan theta over 3. That's its minimum possible value for this equation to work. If it's larger than that, no problem. This will work definitely. But yeah, it needs to be that. Part E, a logic one. The coefficient of mu friction is now made less than the value, so the cylinder both rotates and slips. Indicate whether the translational speed at the bottom is greater than less than to what we calculated earlier. The answer is it should be greater. Why? Because we have a small, or our acceleration is greater because there's less friction. Kinetic friction here is smaller than the static friction that we would have involved. And so we're going to end up with a greater net force down the ramp. Now here's the tricky one, and this one is this is part E, the second one, where a lot of people got this one wrong. Indicate whether the total kinetic energy of the cylinder at the bottom of the inclined plane is greater than, less than, or equal to the total kinetic energy beforehand. And here's where it gets interesting. Because we're dealing with kinetic friction, the force of sliding friction between two moving surfaces, this actually generates heat. Or I could say E dis. Static friction, which is a tough one to think about, never generates heat. Why? Because there's no motion between the two objects. In this case, because as our thing slides down here, I'll put not rotating, this point of contact as it slides is going to be generating heat. What does that do here? The answer is it's going to be less than before because now we have energy dissipated, heat created as it slides for a while down this ramp, which is a really strange idea. With that, have a good night. Work on the textbook problems. Hopefully, they're not too terrible. Some of them involve angular momentum, conservation of angular momentum. We'll move into, with the review day, I'll do a few more AP problems. But take a look at the review sheet, ask me some questions, and I'll post the test a little bit later. With that, have a great night, and we'll talk to you soon. Bye.